I'm really glad to be able to introduce David Dankworth from ExxonMobil. He's the Hydrogen Portfolio Manager for Low Carbon Solutions Technology, and he came here all the way from New Jersey to speak with us, and he's going to be presenting technology enablers for low CI hydrogen at scale.
Hi, thank you. Hopefully the slides will come up. That's me. I have another title here, yes. Okay, it's great to be back here at University of Texas. I think it was about a year ago that I was last up here. And I was actually quite nervous to be in this room for the first time, but today I feel comfortable. There's one thing I've noticed is you guys are all in such a good mood. And it's very lighthearted. Maybe it's because hydrogen's a light element. But all the talks, all the conversations today have been very positive. And it's been really a good day so far. So what can I do to add to that? We heard from Chevron early in the morning. That was a great talk. I really couldn't disagree with anything that he said. What I want to do is represent a little bit of how Exxon sees the hydrogen space. And I want to do a particular focus on technology because I feel like while we're almost there, there's some key gaps in technology that will be needed to fill before we can get to clean hydrogen at scale and really hit all these targets. My current job at ExxonMobil is Hydrogen Portfolio Manager. That doesn't really mean much when you say it, and that's the way all of our titles are. But what it really means is I work between the low carbon solutions business and the technology organization on what are the technologies the business needs to grow and thrive in the hydrogen and ammonia space. And so that includes research and development on new ideas. It includes assessing third-party technology that we're going to bring in for projects. It involves the whole value chain, from production to end use, and all types and colors of hydrogen. So for the last 3 years, I've been immersed in this world and thinking about how do we actually make this happen. For the previous 35 years, I was immersed in process technology for refining mostly. So we were thinking about how do we make low sulfur fuels happen? How do we upgrade crude oil in better and cleaner ways? It's been a big transition to move over to low carbon solutions and to think now about how do we take light hydrocarbons and turn those into zero emissions fuel. So that's really the focus at ExxonMobil. So let's get past this cautionary statement, if you can read this. Which basically means, don't invest, don't buy any stock based on what I tell you. I want to talk a little bit about the low carbon solutions business. ExxonMobil reorganized in 2021, where we used to have 7 or 8 different big, pillars of the company. Now we only have 3: upstream, product solutions, which is chemicals and refining, and low carbon solutions. So low carbon solutions is now the 3rd leg of the entire corporation. It starts small, but the intent is to grow it to be as big as the other 2. And within low carbon solutions, we're focusing on just a few main business lines that match really well with the capabilities of ExxonMobil. And those are carbon capture and storage. So that brings in the subsurface aspects of what we're used to doing. Hydrogen and ammonia, which is really a delivery of a fuel. It's also a way to do that carbon capture centrally and then distribute that product out to customers that don't have to worry about it. We're also launching a lithium business, which was announced maybe, 6-9 months ago, because we believe we can extract lithium from deep brines and do that more efficiently, cleanly, cheaply than anybody else. And so that business is rapidly ramping up. And then longer term, we're working on 2nd and 3rd generation biomass to energy. whether that's with carbon capture and negative emissions, or it's biofuels of, from cellulose and from wood and those kind of things. So the low carbon solutions business is starting from these few things, and we're trying to grow. I'm going to talk a little bit about, in the hydrogen space, kind of the big initiative that we're doing, which is the what we call the Baytown Blue. It's a giant blue hydrogen project in Houston. I'll say a little bit more about that later. So we've seen this, you've seen this, a version of this slide already a couple times. And my only point here, 2 points. One is just remind, if we look at energy transition and we look at the kind of projections out of how hydrogen could play in the energy transition over time, there's a wide range of projections, but it could be up to 400 million tons a year of hydrogen used to, in the energy system of the future. That's about, not quite 10 times more than what we make today. But what I want to focus on, beyond those very large quantities, the end uses. When we talk about energy transition, we're not using hydrogen just as a feedstock anymore. We're not making chemicals out of it only. We're using it for energy, which means we're going into end uses that are not normal. We're switching the fuel in industrial facilities. We're switching the fuel in power plants from natural gas or coal. We're putting it into heavy-duty transportation. So this is where the biggest technology gaps are, is around, are we really ready to put hydrogen into use at these kind of applications at large scale? Now, I use this slide to kind of talk about the landscape around, how production, midstream, and end use kind of fit together. There are different ways to produce hydrogen, and I'm showing the water splitting one off to the right there, but at ExxonMobil we're really focused on the molecule feed basis, where we start with something that has a high energy content, but it has carbon in it, and we want to take that carbon out and then send the hydrogen through. So that means we need that CCS infrastructure to be able to put the CO2 in the ground. Or in the case of methane pyrolysis, we'll reject it as a solid carbon. All these are possible pathways. And in the case of the basic blue hydrogen, the technology is largely there to do it today. So you can build a facility, you can make blue hydrogen today at a very high capture rate, and I'll talk about how we're doing that. The transport part is a little bit harder, especially if you don't have a pipeline, right? So then you have to think about liquefaction. Liquefaction today only works at about 30 tons a day, max scale. That needs to be scaled up. And then as you get into these end uses, right, you have to get the hydrogen to them, and then you have to have devices and systems that can reliably use the hydrogen. So one of the ways that we're trying to deal with the production side of it and those massive quantities is scale. And so you think about 400 million tons a year. Today there's probably a couple hundred SMRs around the world that are making the sort of 90 million tons. You can imagine the future, you don't want to have 10,000 hydrogen plants making the 400 million tons, right? So we need to scale this up, and that also brings the cost down. And so the point of this chart, and you saw this cost thing before where, the blue hydrogen is going to cost more than the gray because you have to put the CO2 in the ground. That costs something. So if nothing else, that's going to make it more expensive. But when you look at this typical scale of, an electrolyzer plant, the biggest one today is about 150 megawatts. That's that little green rectangle there. If you think about a gray hydrogen plant, a typical one today is about 150 million scuffs a day. They could go up to 250. That's that gray rectangle. The plant that we're planning to build in Baytown is the blue rectangle. So it's about 8 times bigger than the biggest SMR, right? We're going to be using ATR technology coupled with cryogenic CO2 capture. And we think those two technologies fit together to give you scale and a high capture rate that we need for this kind of process. But this will be the first time that someone's tried to make hydrogen in this kind of quantity. That's 2,000 tons per day in that blue rectangle, 1 million tons per year. So we dive into that project a little bit more. The idea is to get to 98% plus carbon capture. And on top of that, we're planning to use what we call differentiated natural gas. So we're actually making our Permian assets net zero. The gas that we bring in from the Permian will be essentially zero methane emissions, zero carbon emissions in producing it, which then comes into this hydrogen plant with very low scope 3 from upstream. Combine that with the power import for this project, which is, it's very small compared to the electrolytic hydrogen, but there's still some power needed. All of that power will be with renewable credits. So very low carbon power import, which gives us a very low carbon intensity on the blue hydrogen. And that lets us do things like ship it to Japan as direct burning ammonia in the coal-fired power plants. It will let us convert about 30% of our own facilities in Baytown to hydrogen service. And we have plenty of hydrogen left for others in the Houston region. So the idea here is to create this large source of clean hydrogen that then can spawn all kinds of other uses. So these are the ones that we're kind of initially planning, but you could imagine a transportation delivery hub coming from this. Other folks coming in, taking this hydrogen and using it for various things. I'm looking forward to the high velocity hub discussion later to see how it might play. So if we move away from that production technology for a minute, so into the midstream, hydrogen storage and transport, you really have three options. You can put hydrogen in a pipeline, you can put it in a truck as a liquid, or you can put it in a truck as compressed, or you could build your hydrogen plant right next to the customer, right? So you can do that for one customer, but you can't necessarily reach a lot of them that way. So some version of these transport have to be used. There's a lot of talk about pipelines. Can we convert natural gas pipelines easily to hydrogen? Well, okay, maybe the easily has a question mark on it. But yes, you can. Worst case, you just replace the pipe. New pipelines are rather straightforward, and hydrogen pipelines already exist throughout the Gulf Coast. So there's a network that the major gas companies each have their own network of pipelines. So that's a fairly well-known technology. The opportunities are in this kind of truck delivery, where, as I mentioned, liquefaction is a great way to get hydrogen in a form that will go on a truck. You could put 4 tons of hydrogen on a truck. That's equivalent to a truckload of diesel, just about. The problem is liquefaction is only done at pretty small scale today. 30 tons a day is enough to supply maybe 4 truck stops. So we need better, higher efficiency liquefaction technology and larger scale, which means those machines that are used for that need to be upgraded. So there's opportunities for research in that space to get better machinery, better hydrogen compression. That also applies to pipelines and other things too. All that equipment along the pipeline is currently quite expensive and not very efficient, but it will work. Industrial heat is another place where we need technology. So as I said, one of the main uses that we're aiming for is this industrial heat fuel switching, where you take where you're burning natural gas today and you burn hydrogen tomorrow. So if you think through an industrial facility, typically like a petrochemical facility, you have probably 5 or 6 different kinds of furnaces and boilers in there, each with their own kind of burner technology. So you need a bespoke burner for each one of those that can not only burn 100% hydrogen, But until you have a lot of hydrogen available, it has to be able to switch back to natural gas very quickly in case there's an upset or a loss of hydrogen availability. The good news is these burners are available. So this is an example of a burner from Zeeco. They're a company in Tulsa, Oklahoma. We've been in partnership with them for a long time on low NOx burners. They have burners that will go into most of those services, everything except pyrolysis, olefins pyrolysis furnaces. And ExxonMobil has a proprietary solution for that we're offering. So you could see the picture there, natural gas, hydrogen, same device. The NOx level there is also under 10 ppm. So you really don't have to change your NOx controls either. So the burners are possible in the furnaces. The question mark today is for gas turbines. So there are quite a few gas turbines in an industrial facility that are giving shaft power. They're part of a cogen plant. Those run on natural gas. They're high pressure combustion. They're very short residence time. The turbine manufacturers are a little behind in getting those ready for hydrogen. But we feel like they will be ready in about 2 or 3 years. And we're seeing some small demonstrations already. But that's an area of possible research around this special gas turbine combustion to work with hydrogen and eventually with direct ammonia as well for places where you want to move ammonia as your hydrogen carrier and use it directly. So the other thing I wanted to mention here is as part of our project in Baytown, where I say we're going to convert 30% of our petrochemical facility into hydrogen fuel, we're starting to install these burners already. And we'll start testing them in a few furnaces over the next year or two, so that by the time this thing starts up, we'll have complete commercial viability data to say that these can go and that they work. So this is happening, in real time. I already talked a little bit about mobility. I think the big problem in heavy-duty transportation is, besides the hydrogen liquefaction capacity, is the fact that the fuel cell trucks are not really 100% ready to go into massive scale. I think they're close. But more importantly, the fueling station technology is about 5 times too expensive today. It has a lot of compressors. It has a lot of equipment that needs to be eliminated. So working on this kind of hydrogen fueling station technology is going to be key to activating the heavy-duty transportation market. That's kind of my personal opinion, but I think it's generally true, and it's the thing that's keeping it from activating today is the cost is too high. Hydrogen sells for something like $22 a kilogram in California at the retail stations. That's just a bit higher than what a trucker will tolerate. I had a couple slides here on some advanced technologies. I just really wanted to flash them up to say that there's work out there on further process intensification and kind of crazy ideas for how to make hydrogen in one step to further simplify the process of going from natural gas to hydrogen and CO2. Today's process has about 6 major blocks to it because you want to get the hydrogen and the CO2 as 2 separate products, both very pure, and you don't want to burn anything and let it to the atmosphere in between. So it makes it quite complicated. Some of these ideas like membrane reactors that do separation and reaction at the same time, things that integrate oxygen separation into the process, might be, the modular technologies of the future. And these are very much at its kind of TRL 3-4 today. But we're watching closely in this space to see if there's something that we can start taking towards commercialization with the next 5-10 years. And my last point just is all this is done with a lot of partnership from a lot of parties. Putting a technology together is complicated. You need fundamentals. You need to start with some good ideas. You need very good engineering. And importantly, you need technology demonstrations along the way to get something from TRL 7 to TRL 9 And so we see this as kind of progression here from universities, national labs, companies, and then hopefully our projects. So I'll stop there. I think we may still have 5 minutes for questions. Over here.
On your chart, well, thank you for a very nice talk. You taught me things. That's good. On your chart with pyrolysis, you listed carbon as a co-product, and I have heard complaints that carbon is a waste because there's not a large enough demand for the carbon to be a co-product. Has ExxonMobil thinks they found sufficient demand that it can really be a co-product?
Okay, yeah, that's a good question for pyrolysis. I mean, it's kind of early days on pyrolysis, so no one has done a big-scale project yet to get enough carbon to know what you can do with it. That's one of the problems. But you do see startup companies, let's say Modern Hydrogen, that are making byproduct hydrogen or carbon that can be blended into asphalt and put on roads. So that's fairly useful. I mean, it actually adds the volume to the asphalt. If you have a granular carbon coming out of pyrolysis, that's like sand. So what do you use sand for? You put it in cement, you can maybe use it as a construction material. So we think there are markets that will be big enough and but not really high value, where you could put methane pyrolysis carbon in. You know, it's going to be something, I think, you know, there's at least 40 startups out there, and you know, there's a lot of work going on to identify that.
Thank you for the great talk. I have actually 2 questions regarding the transportation part. One, for making ammonia as the hydrogen carrier, because making ammonia, if you use hybrid rush process, that also itself needs really intense energy. That also itself can release a lot of CO2. I would like to know what process does ExxonMobil use for making ammonia as the carrier from hydrogen? And second, does ExxonMobil use another hydrogen carrier, for example, liquid organic hydrogen carrier, MCH, or other hydrocarbon as the carrier, or not? Thank you.
Okay, yeah, I'll answer the second one first. As of right now, we're focused on ammonia, because we think that's the most straightforward, and it has the highest energy density, and the customer doesn't have to do anything else with it, right? You don't have to return something like the liquid organic carriers, where you have to return the toluene. So that's just our focus for right now. There may be other things that come later. Second question on making ammonia. Ammonia synthesis is actually exothermic. So it actually doesn't need a lot of extra energy because it generates heat within itself. And the ammonia synthesis processes that are out there from multiple licensors are all very advanced. They're like 100 years old, right? So they're quite efficient, they're quite well integrated. And so you need maybe a little bit of extra electric input, but other than that, the plant runs itself, and there's no more emissions. Yeah.
I may have missed it, but you said 30% for the Baytown plant. Is there a projected date when that's going to happen, or a plan of when that would happen? You said you were converting to hydrogen. 30% of the plant would be moving towards that. Is there a date determined, or is it kind of a goal?
Well, that would be when the plant starts up, right? When
Okay.
this blue hydrogen plant starts up, right? It hasn't been FID'd yet. That's maybe next year. Startup is sometimes out in 2029, right? And so we have a few years to install all that equipment. Okay.
I might have missed it, but just wanted to clarify, has Exxon put out any numbers with regards to cost per MTPA for a hydrogen plant versus an LNG plant?
I don't think we would have put out any numbers like that.
Okay.
Yeah, we typically don't talk about how much things cost.
Second question I had was, some of the OEMs in California are providing hydrogen as a solution for some of the cars that they've come out with. Is there any plans, or has Exxon announced anything downstream with regards to making gas stations becoming electric or hydrogen-related product available, eventually working with some OEM?
Right, okay, yeah. The question is, are are we planning to get into the station business? No, we haven't made any announcements like that yet.
Looks like we have a little bit of time. Any more questions?
Very good. Thank you very much.
Thank you.
Enjoy the questions.